that you will power through. Um, Okay, so go ahead and open the slides up at the top. We're going to talk about Earth's magnetic field today, which kind of has something to do with dipoles, but that's not the main thing I really want to talk about. There's an outline there on the second page of what I want to talk about. I want to start with just how electric and magnetic fields are created. Just a brief, we talked about this before, but a little brief overview of how they're created. Um, the forces that they create on charged particles, and then we're going to talk about electric and magnetic dipoles. There's an interesting difference between electric and magnetic dipoles that stems from the fact that electric field lines have beginnings and ends, and magnetic field lines don't, which is a really important difference between the two. And then we'll talk about how Earth's magnetic field is created in the liquid outer core of the Earth and things that happen as a result of that. And then we'll talk about near Earth properties of its magnetic field, compasses and things like that, and then extend out a little bit further to start talking about the magnetosphere, the region of space that is largely controlled by the Earth's magnetic field. And then we'll finish up with several slides talking about the interaction of the magnetosphere with the solar wind, which is really the key thing. The solar wind is the primary actor in shaping and causing the dynamic processes that happen in the magnetosphere, including, of course, the aurora borealis. So we'll just mention that briefly. It's not a talk on the aurora borealis, but we can talk about that afterwards. That's what I did my doctoral thesis on. Oh, more than half a century ago. Is that true? Well, no, not more than half, but anyway, about a half a century ago. So let's go on to slide 3, um, where I want you to talk about the source of electric fields, and we'll just very briefly kind of do the mirror image of this for magnetic fields on the next slide. The source of electric fields is charged particles. If you have charged particles, you have electric fields. Electric field lines run everywhere tangent to the direction of the electric field, which is a vector. It's a vector at every point in space. Electric field lines run through space, always tangent to the direction of electric field at each point. And their spacing, if they're drawn correctly, is an indication, maybe not a perfect indication, but at least a qualitative indication of the strength of the electric field. Crucially, the crucial difference between electric field lines and magnetic field lines is that they start on positive charges and end on negative charges. So over there at the right, you have a couple of pictures showing a positive charge, the source of electric field lines, and a negative charge, the sink of electric field lines. And you can kind of see from the drawings that the electric field is stronger near the charges than it is further away, simply because the field lines um, are spaced more further away, and they have to be because you can't introduce new ones, right? The field lines only start on positive charges, only end on negative charges. So once you've started a field line, you have to keep drawing it until it ends. And necessarily, as those field lines move away from a positive charge, they will get further apart. In fact, they get further apart as the inverse square of the distance, which you don't really see in 2 dimensions, but in 3 dimensions, you would see that. And then I've drawn a picture down there at the bottom, just showing a field line diagram for a somewhat random collection of 3 charges. You can see from the diagram that 2 of those charges are positive charges because field lines are starting on them. You can see that one of them is a bigger charge than the other. Because more field lines start on it than the other. And you can see that one of them is a negative charge because field lines are ending on it. And you can also see that there are more field lines starting in that region than there are ending in that region. So if I were to go further and further away from that, I would still see field lines leaving that region because there's more positive charge in that region than there is negative charge. That's hinting at a thing called Gauss's law, for those of you who may know something about that. So let me stop there and see if there's any comments or questions on that slide. And we'll take a quick look at the. Oh yeah, Chinga's here. He also doesn't do voodoo magic. He likes to. Oh, I see. He's just. He'll people be dumbing. Well, Chinga, I don't know what you mean by that. Okay, he's being silly. All right. No questions on that slide. We will. Oh, by the way, as always, raise your hand. We'll bring you up. You can just hang out up here if you think you might have a question later on or a comment. If this is a particularly interesting topic to you and you suspect you might want to say something, why not come up now and just be ready to stop me when I say something you don't get. I leave that to you. Let's move on to slide 4. We talk about the magnetic field. So the source of magnetic fields in a kind of a, so slide is intended to be very parallel to slide 3. Moving charged particles produce B fields. And the moment I say that, you should say, wait a minute, what do you mean moving charged particles? Moving according to whom? Because according to relativity, there's no such thing as absolute motion. So how can it possibly be that moving charges create B fields? They also produce electric fields, of course, because any charged particle produces an electric field. But when it moves, it produces B field. And the answer to the question, what about relativity, is well, that's partly what relativity was invented to address, is to understand that in fact one person's magnetic field is really another person's electric field, just like one person's space is another person's time in relativity. So those two things are very
I
similar in
love that.
relativity.
Say it one more time, but closer to your mic.
Oh, unfortunately, I'm wearing AirPods, so I can't get any
Ah,
closer today. I'm
all
not
right,
at
never
I'm
mind.
not at home, so I don't have my FM FM mic. But I will say it one more time. One person's magnetic field is another person's electric field, just like one person's time is another person's space. Not to say that that happens 100%, but the two get mixed up when you move relative to somebody else. Part of your time becomes their space and vice versa. Part of your electric field becomes their magnetic field and vice versa. That's what relativity does. So, and I won't say anything more about that right now, but it's another thing to talk about someday. Um, okay, so you've got that on the playback. So that's how they're created. Magnetic field lines, and I'm going to call them B field. And this is one of those jargon things. I say B without blinking an eye. I say B, and I say, oh, magnetic field. A lot of you probably say, why on earth would you call it a B field? And that's just there's historical reasons for that. I don't know what they are, and I don't really care at the moment. But just get used to seeing B field and knowing that that's magnetic field. B field lines run tangent to the direction of B everywhere at every point, just like electric field lines do with E. Um, and their spacing indicates the strength of B, just like the spacing of electric field lines indicates the strength of E. So it's exactly the same as far as that goes. But unlike electric field lines, B field lines do not have beginnings and ends. They loop around electric currents. Sometimes you may have to follow them for a very long time before, maybe forever, until they come back on themselves. They may not even come back on themselves, but they do not have beginnings and ends. That's a really interesting thing about magnetic field lines. They loop around currents in a sense determined by the right hand rule. And there's a drawing there showing if you have a so-called current carrying wire, current carrying conductor, carrying positive charge upward or negative charge downward, either one of those is an upward current. It turns out that in wires, the thing that actually moves is electric field. And as Benjamin knows, the energy in a wire flows outside the wire, but that's also another topic for another day. Um, the current flow that I'm showing there is flowing upward. I'm just telling you that. That could be because of positive charge flowing upward, but if it's a real wire, it is actually because of negative charge flowing downward. And the way you determine the magnetic field is, first of all, to know that it loops around the wire in circles or circular kinds of things. And it does so in a sense that's determined by using your right hand to do what is shown in that diagram. You wrap your fingers around the wire in such a way that your right thumb points in the direction of current, and that'll tell you the direction that the magnetic field lines are running there. So let me stop there for just a moment, see if there's any comments or questions on that.
Very quickly and anticlimactically, the reason why B is used for a magnetic field, or to be exact, magnetic flux density, and it is completely because James Maxwell, as he was writing, he was assigning random letters for whatever variables he has. And so he has B for magnetic field, magnetic flux density, simply because it came before magnetic field strength, which he assigned H for example. So
Well, then
it's completely.
why wasn't it G? Should have been G if it was going to be before H. Oh,
Oh
G was
no,
already
it
taken.
was like 5 stages before. Other variables have. It's completely silly. It has nothing to do. I used to think that it has to do with something in German, but as I'm learning German now, this has nothing to do with it. It's just random variable assignment.
Well, that's interesting. I'm not sure I believe you, but I don't think I've ever looked it up, and I don't have an alternate story. So for now, we'll just go with
Yeah,
Maxwell
believe
made it up
me, that's what
randomly.
you should do. And then Benjamin's gonna say, "Oh, these scientists, they're like a religion. They believe each other without checking." Yes, exactly.
Yeah, and we've been joined by VP. I don't know if you came up to ask a question or make a comment, VP, but you're welcome in any event.
Yeah, appreciate that. No, I'm just when I hear something, I just want to be able to respond whenever I
Good.
hear something interesting.
All right.
So
Excellent.
I had a quick observation, which I don't know whether it actually means anything, and that's that it's interesting that this electromagnetic field uses the right hand rule, and I'm kind of curious what's the big deal about the right hand rule, because in biology, you know, DNA is a right-handed helix, alpha helices in proteins are right-handed. So really, every time we see a helical or going around thing in nature, it ends up being right-handed. And so that was an observation without any explanation, or it was just an oh golly gee, isn't that neat kind of
Yeah.
thing.
Well, I think in the case of DNA, I mean, it really is one way and not the other. But in every instance that I know of in physics, it's just an arbitrary choice. We could have defined the magnetic field to go the other way. That would have been fine. And if so, then we'd have to use our left hand. Once you have decided on a few right hand conventions, a lot of other right hand conventions are then dictated. But ultimately, there's no. Ultimately, it's arbitrary. There is an original choice of right-handedness that, in physics at least, is arbitrary. I
Yeah,
think that's fair to
thanks.
say.
Yeah, yeah.
That may not be quite fair to say when you talk about helicity of neutrinos, et cetera, and antineutrinos, et cetera. I think there you have a genuine one way or the other kind of a thing. But certainly in the stuff that we're talking about here, it's completely arbitrary.
Yeah, I mean, I
Yeah,
wouldn't be surprised if we someday find out that the right-handedness of the magnetic field kind of forced DNA and amino acids, you know, because we do have left-handed DNA. It's called bDNA,
right,
but it's not found in nature. It's made in the lab.
right. But in that,
And,
but I think
but
once
it,
again, you go ahead.
yeah. No, I was just gonna say, if magnetic field was left-handed, then who knows? Maybe bDNA would have been the dominant DNA in
See, I'm
biology.
pretty sure that's not the case because the left-handedness of the magnetic field is arbitrary. And the helicity of the DNA is not. It's what it is. So, um, Yeah. Anyway,
All right.
let's see. Okay, so on slide 5, I'm going to talk about the effects of magnetic and electric fields. There's no reason to have them unless they have some observable effects. And the effects are these, that electric fields produce forces on electric charges in the direction given by the charge that's having the force exerted on it, times the vector E. So if I have a positive charge in an electric field, it will feel a force in the direction of the electric field. If I have a negative charge in an electric field, it will experience a force opposite the direction of the electric field. So there's a diagram there showing a positive charge. It doesn't say it, but it is apparently a positive charge moving to the right through a downward electric field, which, because it's a downward electric field and a positive charge, it produces a downward force on the particle, just like gravity would, and the particle follows a trajectory that is just like the trajectory of a particle in the gravitational field. You know, in your backyard, when you throw a ball horizontally, it will do the same thing because there's a downward force on it and it has some motion to the right in this case. So electric fields are pretty simple. It's just that. Magnetic fields are significantly more complicated. They produce, first of all, they produce forces on moving electric charges. And once again, we have to go, what? Moving? Like, what do you mean moving? And the answer is the same one I gave before. Um, I mean moving because all that matters is who's actually doing the calculation. Somebody else to do the same calculation, they'll get the results to agree with what they see, but they'll have different ideas.
Yeah, I think you went into the Matrix.
Yeah, I was wondering if I lost him or he was lost.
Oh no, he's interacting with some magnetic fields at the moment. Once he stops moving, he can come
Yes.
back to our frame of reference.
Okay. Yeah, he went into an energy vortex. Sorry.
I was just gonna say that would be a good feature on the app if immediately they just like lit up your screen in red or something to know that it's like not you or that it is you. You know what I'm saying?
I'm just curious. Is I know the Earth spins, but there's probably 2 points at the very top and the bottom of the Earth where if you're standing on it, y- technically you wouldn't be like spinning. Is that right?
Yeah, but these are different from the magnetic poles. So what you're thinking about is the point where the axis of the Earth passes through the North and the South Pole. That's not the same point, although it's very close geographically, but it's not the same point as the North magnetic pole and the South magnetic. I'm sure John will get to it in his presentation if he ever manages to come back.
That'd be a good thought experiment at what it would if there really was a pole that was going through the earth and you can see it. How small would that pole have to be that we so call say isn't spinning?
I'm
I,
kind
I
of curious. I'm kind of curious. Like, is there anything different if you're like right on standing like right in that lat long? Like, can you observe anything different than if you were standing, you know, anywhere else on the Earth?
I'm not sure if practically you can, but mathematically speaking, the Coriolis force over there will be the weakest. Now, whether this is experimentally verifiable, like if you stand 2 meters away from that point, would you be able to find out? I'm not sure. Like these forces are already weak enough that we don't really feel them in daily life. These things affect very large things like the weather and the winds and all that stuff. So if I'm sure some physicists who do very careful work, which I totally don't, maybe they have a better idea of how precise they can pinpoint that geographic location. And to determine the magnetic pole, all you have to have is a compass. And then when the compass stops pointing you to a certain location, then you know that you are very close, if not exactly on top of the magnetic pole. And we know for certain that these 2 points are different. I think the magnetic pole today is somewhere over Greenland, whereas the geographic North Pole is somewhere else,
Okay, that's
somewhere in
pretty,
the.
that's
Oh, here he
complicated.
is.
Yeah, go ahead.
Oh
Sorry.
no, I was just filling your shoes, sir. You have some questions to answer.
Oh, okay, good. What are the questions?
V was asking about the North magnetic pole and the point where you would not feel any rotation forces or rotation effects from the Earth's rotation around itself.
Yeah, good. Save that question. We will definitely get there. I'll try to remember myself, but we'll definitely get there. That's coming up soon. Okay, any other questions on that? I mean, I know that it's not terribly important. It is going to be important to understand, and I'll just say this, the net result of this, the only thing that's really important for understanding the magnetosphere is that particles describe these helical paths around magnetic field lines, and in a sense they kind of get locked to a particular field line. You can kind of think of that particle in that diagram.
Wait a minute, John.
Hmm.
Do you realize we didn't have you for about 5 minutes?
Oh no,
Oh,
I
really?
didn't.
Yeah.
Oh
Hold up,
shoot, I'm
hold up, hold
sorry.
up. Were you hearing me when I was speaking? Did you hear V? Did you hear
I
anyone?
heard you. No, I'm sorry, I heard you at the very end, but I did not hear
Oh,
anything.
Yeah.
I don't know what
yeah.
happened there.
So you kind
Good
of
catch,
need
Sam.
to, we're still on slide 4. Uh,
Oh, okay.
Slide 5,
yeah.
actually. So you
Do
were
we?
talking about moving charges, and then you said what?
Oh
Moving
yeah.
in what reference? That's it.
Yeah.
Did you hear me talk about the electric field, the trajectory of the charge
No.
in the
Nope.
electric field?
No, no, no.
Nope.
Okay. Oh, sorry. Wow, that's really too bad. I'm so sorry. Um, yeah. Oh, and you probably chimed in, and I didn't. I don't know what happened. I always have a good connection here. Somehow I didn't. Okay. So back to slide 5 then. So electric fields produce forces on electric charges in the direction of Q times E. That means that if I have a positive charge in an electric field, the force is in the direction of the electric field. If I have a negative charge in an electric field, the force is opposite the direction of the electric field. So the diagram there on the right shows a positive charge in a downward electric field, therefore producing a downward force on that particle, much like gravity would if it were a ball being thrown horizontally. And as a result of being thrown horizontally, it curves downward due to that force that's changing its velocity in the downward direction. And in fact, in that particular case there, it would be describing a parabolic arc, just like a thrown ball would. It's exactly the same mathematics in that case. So that's pretty easy. I'm still uh, audible.
Yes. Here.
Okay, good. Moving on to the second part, B fields. B fields produce this much more complicated thing. The force they produce forces on moving electric charges. Once again, we stop for a moment and say, "Moving? What are you talking about?" And the answer is the same as it was before. Yeah, it matters who's doing the observing. And one person's magnetic force will be another person's electric force because the charge may or may not be moving in that other person's reference frame. But it all works out if you do your relativity correctly. In whatever frame you're doing it, the force will be in the direction of the charge times this what's so-called cross product of the velocity and the magnetic field. And how does that work? So cross products are weird. They once again call on, they have a handedness to them. And once again, we employ the right hand rule for arbitrary reasons, just because of the way we define things. Um, but that Q times V represents a current. If you have a positive charge moving in some direction, the electric current is in that direction. If you have a negative charge moving in some direction, the electric current is opposite that direction, opposite the velocity. But whatever that current is, whatever you get for Q times V, that is the current. And what you do is you take your right thumb and you point it in that direction. So right down below there, you see the blue arrow, right thumb, pointed in the direction of Q times V, the current. And then you take the fingers of your right hand, point them in the direction of the magnetic field, and having done that, the force, the magnetic force on the particle is in the direction given by that green arrow outward from your palm. So it's a very three-dimensional, kind of a weird thing, the cross product. And just to show an example of that, the helical path over there on the right, um, if you just let's just start off at the beginning, where it shows the charge there, the charge at that point is moving kind of upward and to the right. Point your thumb in that direction. That's the current. Positive charge moving in that direction. That's the current. So point your thumb upward and to the right along its trajectory there. Then take your fingers, contort yourself so that you can point the fingers of your right hand in the direction of the magnetic field, and you'll see that the force acting on that charge is kind of, into the page and down a little bit, causing the trajectory to bend in the direction that you see because it's trying to force it kind of that way. But the problem now is that once it has changed its direction, V itself is different, so you have to do it again. And when you do it again, you'll see that the force is still kind of down toward, if you just take that helical path and imagine the central axis of that helical path, I think you'll see that the force is always at every point on that helical path directed toward the axis of that helical path. And you can kind of see how the helical path is generated by that. What happens is that the electron or the charged particle uh, uh, continues to have whatever velocity it has along the magnetic field, but the velocity component perpendicular to the magnetic field gets bent into a circle. If it didn't have any velocity along the magnetic field, it would just go around in a circle. But if it does have some velocity along the magnetic field relative to you, then it will move along the magnetic field while it's executing circles. Of course, you could always just move with it along the magnetic field, and then you'd see it simply executing circles around the field. Um, Now, all of that, I'll stop here for a second, in a second, but I just want to say that's all kind of complicated, the cross product thing, et cetera. But the real takeaway, the thing you need to take away from this is that charged particles always execute these helical paths around magnetic fields, and in fact can really be considered to be locked to the magnetic field right at the center of that path. They follow along, wrapping spirally around that particular magnetic field line. This isn't exactly right. There's times when time changing magnetic fields, things get a little more complicated. But if you just have a static field, that's what particles do. They just describe helical paths along the magnetic field as if they were locked to the magnetic field line in the center. And I will stop. And I hope you heard it at that time and see if there's questions. And I apologize once again for dropping out for so long.
Okay, maybe you will cover this. I think you would, but just let me ask this.
Hmm.
If magnetic fields only affect moving charges, and if electric fields affect charges in general, then what happens in a permanent magnet, something like a compass? It's not moving, yet you put it in a magnetic field and somehow it starts moving.
Right. So I could just say, Benjamin would love this. It's quantum mechanics. Uh, wait,
Oh,
what's
but
really
then quantum mechanics is fake, John. No.
so it's profitable to just think of it this way. Atoms, in some sense, have electrons orbiting them. That's a classical picture, so it doesn't really work. And they're also spinning, but they're point particles, so that doesn't, it's not clear what it means to spin when you're a point particle. All of those things are kind of weird, but the kind of classical picture that we have of permanent permanent magnets is that the magnetism comes from spinning or orbiting charge in at the atomic level. And I hope you can kind of see how that could work. There's a problem with that. Quantum mechanics kind of makes that picture problematic, but it still kind of explains things the same way. Atoms have magnetic dipole moments, which we'll get to in a moment here, both because of the orbiting electrons and because of the spinning electrons, and also because of spinning nucleons. So there's lots of processes at the atomic level that do that. And a permanent magnet is always the result of magnetism that emanates from these kind of spinning orbiting processes, if you want, at the atomic level. So that's what a permanent magnet is. Of course, an electromagnet it's actually has real currents going around and around and around, some like a pencil or anything else, creating a very strong magnetic field, dipole kind of field, as we'll talk about here in a moment. Does that help at all?
Yeah, sure. Keep going.
Okay. And welcome, Chinga. And let's see, we had somebody else on stage, I think, a moment ago. Maybe we didn't. Oh, Pro was up here, I think. Did he leave again? Yeah. All right. All right, so let's move on to slide 6, where we talk about dipoles, and this is really the important thing. An electric dipole. There are electric dipoles and magnetic dipoles, and they're really important. Electric dipoles, in particular, in chemistry, as Sam talked about yesterday. Um, an electric dipole, which is measured in terms of the product of a charge and a distance, and measured in units of Coulomb meters. The unit of charge is Coulomb, unit of distance is meters. So electric dipoles measured in Coulomb meters is created by two equal and opposite charges, plus Q and minus Q, separated by a distance d. And so the picture at the left below shows an electric dipole. You see electric field lines leaving the positive charge on top, curving around and ending on the negative charge on the bottom. Every electric field line that leaves the top one ends on the bottom one because they're equal and opposite charges. So just as many field lines start on the positive as end on the negative. And you can kind of see what that character is. I think you've seen dipole type field diagrams a lot. And I kind of like the fact that this is so roughly drawn. That'll get handy when we talk about the Earth's magnetic field, because the Earth's magnetic field is merely kind of dipolish. But you see, the character is that idea, especially out at the fringes, where the field lines leave the positive, kind of bend toward the negative, come around, and finally dart into the negative charge. A magnetic dipole is created by a current flowing around a loop, and it's measured in terms of the product of the current and the area of that loop. So magnetic dipoles are measured in amp meters squared, the current ampere times the area of the loop meters squared. And it's created by a current I flowing around. I said current I, there I go again, right? Why is it current I don't know. It is. I don't think that's Maxwell's fault, but might be.
Yeah, the whole thing. I, J, the whole series. He started. I'm not sure what A is for, but B is for the magnetic field. C is for Coulomb, I think. D is for displacement. E is for electric field. He started with
Yes.
them, one by one.
Well, now I think you're telling a little bit of a story, but once again, I don't have a better one, so we'll go with it for the moment. Um, So that's a magnetic dipole. And you can kind of see what's happening there. In this particular case, you have a current, doesn't show it, but the current in that thing, assuming the lower part of that loop is toward us and the upper part of that loop is away from us, we're kind of looking down on that loop, the current would be flowing kind of counterclockwise around. It doesn't show it there, but that current would have to be flowing counterclockwise. And if you point your thumb of your right hand at any point around along that loop, you'll see that your fingers come up through the interior of the loop and then wrap around the outside. So every part of that loop is creating an upward field within the loop. and then that field goes around the loop, comes back, and joins up with the field line where it started. You notice that unlike the electric dipole, magnetic field lines, because magnetic field lines don't have starts and ends, it's a different field line configuration, especially in between the charges compared with in the loop. In the electric dipole, the field between the two charges is downward. In the magnetic dipole, the field at the center there is upward. But if you look out at the fringes of the field, they look basically identical. They're both at distance. They both have the same geometry, loop field lines that come up, loop around, come back together and go in. It's just what happens right at the center. And in most cases that we actually talk about in atomic physics, et cetera, these magnetic dipoles, these loops are really small, and the separations between the charges really small. So you don't even see that weirdness at the center. All you see is the far field, which looks identical in both cases. You have a dipole field in the far field. So let me stop there for a moment.
So maybe you can help me out here. Whenever I am forced to explain or teach some of this, I always explain these maps as if they are altitude maps. Is this analogy completely fair, or is there something missing? Because
Well, when you
if you just you know that the potential field lines, they're kind of the same thing as when you have a map and you say, oh, it's 100 meters, 200 meters, 300 meters. Is it similar, or is this
Like
analogy
a
not fair?
topo map? Is that
Yeah, yeah,
is
yeah.
that what you're saying? Yeah.
Topo
the
map, you
topo
called it
map,
topo? Yeah,
hmm
okay.
yeah,
Yeah, topographical map that show lines of same elevation. And so you know that the distance between each two line is like 200 feet or 100 feet, depending on who the map
right.
maker was. Yeah.
And so with a topo map, what you do is to know the direction of kind of the gravitational force, the direction a ball would roll if you let it go. You know it's going to roll perpendicular to those lines, not in the direction of those lines. The kind of effective gravitational force is perpendicular to the topographic lines, and you can do that with the electric field. If you just imagine taking that diagram on the left and draw little dotted lines, say really close to the positive charge, you can draw essentially little circular dotted lines, and the field will everywhere be perpendicular to those circular those dotted circles, I should say. Now, as you get further away from the field, they're not circles anymore, but you can do that. Effectively, the height is very high near the positive charge and very low near the negative charge. But you could imagine what a topographic map would look like there. Lots of circles around the positive charge, a peak going down and down. There'd be one line that goes straight across the middle, and then there'd be kind of things wrapping around the negative charge that are getting lower and lower and lower. If that middle was sea level, then everything on the bottom half would actually be equipotentials at lower than sea level, to going down to a very, very low negative height at the negative charge. So you can do that kind of thing with the electric field. You can't do that with the magnetic field because you get into MC Escher territory. How do you go down, 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 and end up exactly where you started?
Oh, I see. Okay.
Right? So there's no such thing as a scalar potential for the magnetic field as there is for the electric field. It does turn out to be a thing called a vector potential, which involves cross products and all these kinds of things, but we really, really don't want to go there.
Yeah, I see what you mean. Thanks.
Yeah, good. No, that was a good question.
I
And
want
I
to
think
go
that
there. Can I go
uh,
there?
you always want to go somewhere, Chinga. Go ahead.
No, I'm just kidding.
I know you're always kidding.
I have a
And
question
you
though.
want
I have a question. So their
to?
electric field always has a magnetic field, but does a magnetic field ever have an electric current or no?
Well, so once again, electric fields are created anytime you have charges. Magnetic fields are only created when those charges move, and that's weird because you can make them move by just going into a different reference frame. That's not the frame in which they're not moving, right? Just change your reference frame, and all of a sudden they're moving, and all of a sudden you have a magnetic field. So that's all pretty weird. Um, you asked something else, but I don't know. I don't think I addressed it. But
I
anyway, there's
said, does
that.
a magnetic field ever have an electric field?
Oh, so yeah, that's a weird way of asking it, but it is the case. Maxwell's equations do in a form that we're not going to talk about at all today. When you have a changing magnetic field, that produces an electric field. And when you have a changing electric field, that produces a magnetic field. So it's not that electric and magnetic fields have each other, but changing E fields or B fields do produce B fields and E fields respectively. And I think Elia had something to say. Elia, go ahead. Welcome to the stage. And what would you like to say?
I wanted to ask a question about the sec.
Oh, oh, you're breaking up, Elia.
All right,
You've
let me
got an
try this again. I
intermittent.
said I wanted to ask a question about the first page of the document.
Okay.
All right. It shows three different diagrams: a magnetic field, an electric field, and apparently from the but the positive charge is kind of similar to acts similarly to the north pole of a magnet, as the magnetic field goes out of the north pole and the positive charge and into the south pole or the negative
Right.
charge. Thank you. So I got this right. Okay, and then there is a diagram of the inner core and the outer core of planet Earth, right? But
Yeah, let me just stop you for a second. I did make the mistake of not kind of pointing to them. They were really more intended as just kind of artwork at this point. We are going to get back to those very, very quickly here.
so we cannot take them as guidelines because to me it sounds like the way the magnetic field is behaving around the core of the Earth is kind of opposite to the diagrams shown above, as it is going into the north pole of the Earth and out of the
Mm.
south pole, and this is what not how
Oh,
it should be, right? Should be the
no, that
opposite,
is the
no?
way. I mean, that is a thing, of course, and people often make this point. The north, the magnetic pole that is at the northern geographic end of the Earth is a south magnetic pole.
Interesting. Ah,
Yeah.
that definitely cleared it up. Thank you so much.
Yeah. And we'll talk about that here very quickly. A lot of people, kind of avoid even talking about that by just saying the magnetic North Pole. They call it the magnetic North Pole to avoid having to point out that it is a south. It is a magnetic south. It is a south
Geographic South Pole.
magnetic
Thank you.
pole. Yeah. Yeah, but we will talk more about that in on the very next slide, or well, like slide after that, I guess. Yeah. Okay, so any other questions, I guess, on slide 6 before we move on? All right, well, so let's move on to slide 7. Um, where does the magnetic field of the Earth come from? This is complicated stuff. I certainly won't claim to understand it. I think there are very few people who would claim to understand it, but there are people who have a better understanding than I do. And I'll talk a little bit about why it's so hard to understand here in a moment too. One thing we do know is that the Earth has a liquid, has a core, the outer part of which is liquid and presumably iron. I don't know how we would know that for sure, but maybe we do, just because that's what the Earth is made of primarily, and that's what sinks to the bottom. So we got liquid iron outer core around a solid iron inner core. And the inner core is under high pressure. It's got a lot of radioactive stuff in it. It's generating enormous amounts of heat. That heat moves out from the out inner core through the liquid outer core to the mantle. And that liquid iron core then is subject to all sorts of forces, things that make it do things. Convection currents because of the need to transfer heat from the solid inner core to the mantle. Entrainment by the rotational motion of its boundaries. The Earth is rotating, and a liquid is always entrained to some extent by the motion of boundaries. It's subject to Coriolis forces too, because of the rotation of the Earth. There are these in the rotating reference frame of the Earth, subject to Coriolis forces, and all of those serve to move what is a highly conducting liquid through the pre-existing, and I put a little question mark there, we'll come back to that in a moment, magnetic field of the Earth. Whenever a conductor moves through a magnetic field, you induce currents in that inductor. This is how generators work, by making coils of currents, coils of wire rotate very quickly in the presence of a magnetic field. That's how you generate electrical energy, by inducing those currents. And in this case, those inducing currents self-consistently generate slash sustain the magnetic field that is causing those currents in the first place. And this is a thing that happens. There are magnetohydrodynamic generators that for which you apply some external magnetic field, and the process of forcing conductors to move through that field causes currents that intensify and sustain, not just sustain, but intensify that field. So the process works. The geometry, in the specific geometry in which it works, is complicated in the core because of all of the varying things, the convection currents, the rotation, the entrainment from the rotation, and the Coriolis forces due to that. And I could probably say more if I spent more time kind of studying it myself, but I'm just going to kind of stop here to say, well, I won't stop quite here. I will point out that what does end up there are things called Taylor columns. If you look up Taylor columns, I think you'll see that there is at least some evidence for this happening, that the net result of all this convection, Coriolis forces, entrainments, et cetera, to create kind of these little spiraling currents in this geodynamo, that do sustain and amplify, maybe, or at least create self-consistently the field that is in it is in the first place generating those currents. It's a very weird thing, and it's fair to say that that mechanism is both complicated and certainly not perfectly understood. At least in part, it's not perfectly understood, because if it's clearly chaotic dynamics is something that we've learned a lot about over the last 30 or 40 years. And the dynamics of the geodynamo is clearly a chaotic system, as indicated by magnetic field reversals that we know happen. I was looking this up. I think I was talking about this with Andy the other day. And I think I had suggested maybe they were happening every 10,000 years. Turns out we know of something like 183 magnetic reversals due to locked in magnetic field in the geological record over the course of, I think it's like 8 million years, 80 million years, 8 million, 8 must be 80 million years. So that they happen kind of on average every 500,000 years, but not at all periodically. There's, unlike the solar cycle, which is 11 years, right? Every 11 years, the sunspot cycle repeats. Every 22 years, the full magnetic cycle of the sun repeats. The sunspot cycle happens on each half of that magnetic cycle. That's a very stable, steady, non-chaotic. There may be chaotic elements to it, but it's not chaotic. The generation of the magnetic field in the core is definitely a chaotic process because of these reversals, which occur at time frames that have no regularity, presumably can't be predicted, because they're a butterfly effect kind of a thing. There's a tiny little changes in initial circumstances, making enormous differences down the line. And that chaotic dynamics makes it really hard to understand. So let me stop there. Let's see if there's any comments or questions or scoldings. This is the place where the flat earthers come in and say, yeah, you guys don't understand that at all. And that's not completely untrue, but it's also not completely true. Go ahead, anybody. Ilya. Oh,
Yeah,
you were
just
finished.
Oh,
go
sorry.
ahead.
Yeah, I just wanted to mention something that has to do with history in relation to what you were saying, John, about the sun. Ancient Egyptians knew about those cycles, those solar cycles, because they affected the way the Nile flooded, and they have certain kind of meters that measured the Nile deep holes in the ground with some sort of like measurement, huge measurement kind of stone in the middle that measures that, and that's quite interesting. We're talking about probably 1,000 something years BC, and people know about that, ancient Egyptians. So just felt like.
Well, well, I'd be interested in seeing a link for that. I'd be a little surprised if the solar cycle has a fingerprint in things like the depth of the Nile or something, but I won't just outright say I
That'll
don't.
come your way in a second.
Okay, good. Anybody else?
Yeah,
Shamash, you had something. Yeah.
I just wanted to circle back to this question about why is the North Pole a south magnetic actual
Mm,
pole?
hmm.
And oh, you have it on the slide?
It's on the next slide.
Yeah,
Yeah.
never mind then. Go ahead.
Okay. Anybody else? Okay, so let's just talk about the near Earth magnetic field. We were talking about the kind of field generation in the core. Now let's talk about the magnetic field near the Earth's surface. Near the Earth's surface, it's a magnetic. It's pretty well but far from perfectly approximated as a dipole field. As long as you stay pretty close to the Earth within a few Earth radii of the Earth, it's pretty well approximated by a magnetic field. The field lines come out of the southern geographic region and dive into the northern geographic region. And that means just that fact means that the north end of the Earth is essentially the south magnetic pole, because that's what field lines. I guess I didn't say that before. You have to kind of look by analogy. I should have said this. I didn't say this, and it's critically important. In the case of magnetism, we talk the North Pole plays the role of positive charge in an electric dipole. That's a critical piece of information. That's just what we mean by a North Pole. The North Pole of a magnetic dipole is the end that the field lines appear to come from. We already know they don't, right? They just kind of go around in loops. But in that central region, the magnetic field lines go from south to north. And then in the external region, they loop around from the North Pole to the South Pole, because by definition, the North Pole plays the role of positive charges in electricity, and the South Pole plays the role of negative charges. So does that? I think that might help with that. That was a crucial piece of information that I didn't include before. Now you might ask, so why is it? So what is a compass doing? And we'll get to that on the next slide. So hold that question in abeyance as well. So it is basically a dipole field. The dipole is kind of canted off of the Earth's axis. It's not perfectly centered in the Earth. And that bottom diagram, if you blow up that slide, if you can, you don't have to, but it shows the fact that the magnetic field lines emerge from a wandering north magnetic pole and go. Then that's near the south geographic pole. And they dive into an also wandering south magnetic pole that's near the North Geographic Pole. And you probably know that those magnetic poles wander. They wander significantly on scales of human lifetimes. Over the course of a lifetime, runways on airports have to be relabeled, because they're supposed to tell you the nearest 10 degrees of the magnetic field. And when the magnetic field changes, and it changes a lot, um, runways sometimes have to be relabeled. I don't know if they actually do that. Benjamin maybe knows. I think they really are relabeling some. Is that right, Benjamin? Oh, is he here? Oh, Andy knows too.
I believe they do.
Yeah,
Yeah.
yeah, there are runways at some airports I'm familiar with that have been renumbered
Yeah.
recently.
So So it's really, I mean, it's another kind of indicator of just what a dynamic and in fact chaotic process the generation mechanism is. The field of the earth is changing all the time, and people have to kind of keep track of that for various reasons. Um, if you look at that diagram at the bottom closely, you'll see that there are two kinds of poles indicated, neither of which are measured. They come from models of the magnetic field. Usually, when we talk, for instance, about the North Magnetic Pole, we mean the place near the North Geographic Pole, where the magnetic field is vertical. That's the place where magnetic field lines go straight down vertically, perpendicular to the surface of the Earth. That's usually the place that we talk about as the magnetic pole. And it has wandered enormously. It's been wandering around in the north of Canada for hundreds of years. But over the last 20 or 30 years, it has taken off, moving kind of toward the North Pole, getting very close to the North Pole last year and continuing probably over to northern Russia pretty soon. A lot of people think this may be a precursor of another magnetic reversal because we are currently overdue for a magnetic reversal, and that'll be interesting to see. I may be happy that I'm not here when that happens. You might too, because it probably won't happen in your lifetime, but you never
It's
know.
gonna hurt.
Say again.
Is it gonna hurt?
It's gonna hurt. Probably. Well, actually, we don't know. That's actually another thing. We don't really know. It'll hurt or not, kind of depending on how it happens. If the poles just kind of keep wandering and end up in the south and the north, coming from the north to the south, coming from the south to the north, then we'll probably be okay, basically. Except there'll be some weird auroras for a while, bunch of stuff like that. But if it reverses by just kind of going to zero and then coming back again in the opposite direction, um, hold on to your hats. That won't be fun because we won't have a shield from cosmic rays.
You know, I don't know if this, maybe I'm totally off here, but like in the Bible where it says Adam ate of the fruit, and then people said, oh, you know, there couldn't have been a tree there, and there couldn't have been no fruit there, and then somebody I think said something about how the earth does something funny every now and then, so where that place was back then might not have been the same place as where it is now. Is that kind of what you're talking about?
Well, I am certainly not interpreting scripture or anything else, but you're free to do that. Yeah, no, I would say, I mean, effectively, no, nothing I've said has anything specifically to do with that. But I don't mind people interpreting things however they want. Okay. Um, let's move on then to talk about compasses a little bit on slide 9. So what does a compass do? A compass is a magnetic dipole. It has a north pole and a south pole. And the north pole of a compass needle is the one that points north. That's in fact why it's called a north pole. That's where the word north pole comes from, because the ancients had these lodestones that they found empirically, could kind of help them navigate. They kind of always pointed north, and you fashioned little needles out of them or something, suspended them in such a way, and one side of them would point north, and they called that the North Pole. So that's where the North Pole of a magnetic dipole comes from. But North Poles are attracted to south poles, just like positive charges are attracted to negative charges. So the reason a compass works, the reason the North Pole points north, is because there's a South Pole up there. That's why it does that. Um, and so that's an indication. You can kind of see the direction of the magnetic field lines. Dipoles align themselves with the magnetic field line, with the North Pole pointing in the direction of the field and the South Pole pointing opposite the direction of the field. There's a bunch of little compass needles shown in that diagram upper right. The diagram lower, diagram at the bottom is a magnetic deviation map, and it shows you places that are red are places where compass needles point a little bit to the east of north, or to the, maybe I should say to the, yeah, I should say that, yeah, east of north, I guess. And places that are blue are places where compass needles point a little to the west of north. So in western United States and Canada, western Canada, Alaska, compass needles tend to point a little east of north, and there are equipotential lines there, if you want, lines of equal deviation embedded within those red and blue areas. With a map like this and a compass needle, as long as you know where you are, you can always correct the compass reading to get the direction to true north. You simply find out where you are, see how far off north a compass needle points there, and then correct your compass needle reading accordingly, and you get north. But these deviation maps have to be updated all the time because they're changing relatively quickly, especially right now. This is, I think, a map that's good for like 2020 or something, but it's changing very quickly. So if you care to be accurate, you either get a better updated maps or you just stop using compasses and go to GPS, I guess. So, any comments, questions on that one?
Do you have any idea how they update these maps? Like, is it satellites, or is it, because it's kind of a big hurdle to actually do it? I don't know.
Well, I think it's pretty well automated. There are stations all over the planet measuring the magnetic field and knowing for sure, because you know what the geographic directions are, how much that magnetic field is, both dipping, but it's out of horizontalness and it's out of northness, if you want, right? How much it deviates horizontally and how much it dips. That's a dip angle, is the angle that the magnetic field makes with the horizontal plane. So that's another thing. People don't usually care about that, but that's another thing that these magnetic field stations measure. And once you've measured those at 10,000 stations around the world, you just feed it into a computer and the computer generates maps like
Yeah,
this.
but but
That's not hard.
you must have stations in the sea as well. Like, most of the surface is ocean.
I think there are. I wouldn't be at all surprised if there are buoys, in the network. But it might also be done, maybe with ships that sail around them occasionally. I don't know how it's done. Um, but I'm sure the process of making the map itself is automated based on the data that they collect. One could probably do a reasonable job even with just nothing but land-based and island-based measurements. But I think I wouldn't be surprised if there's ocean buoys doing this as well.
And you said the dip angle is to the horizontal, but we know the horizon's an optical illusion, right?
Yes, some people do know
According
that.
to,
All right, yeah, that's one of those things that now you're going to get me into a discussion of knowledge versus belief, I guess. But I won't go there this right now. Okay, so finally, the magnetosphere. The last few slides, that's 5 slides, are about the magnetosphere. And on slide 10, I want to talk about this. Is really important. Any discussion of the Earth's magnetosphere has to begin with an understanding of how charged particles move in magnetic fields, and especially this concept of magnetic mirroring. We already saw that charged particles spiral around and, in some sense, are locked to magnetic field lines. But we didn't talk last time when we saw this earlier. We didn't talk about what happens when the field lines actually change in strength. If I have converging field lines, as are shown in this diagram, the field itself is getting stronger. And what happens really is that the not only is the helix locked to the kind of central magnetic field, but its radius is kind of locked to the field lines that it runs around. And so as the field lines converge, the area of the circle that it's executing around that central one gets smaller and smaller, and the amount of what do I want to say? Yeah, well, the amount of motion along the field changes. So what happens? It's easy to show that the along the field line motion slows as the field lines converge, eventually stops at a place called the mirror point, and then reverses. So the particle comes spiraling in, gets to a mirror point, and then spirals back out in the direction that it came from. That's very, the physics of this is really analogous to sending to launching a bouncy ball into a very sharp wedge. If you imagine doing that, the ball would bounce off the top part of the wedge, then deflect down, bounce off the bottom part of the wedge, bounce again off the top part, etc. There'd come a place where it's just bouncing vertically, at which point the wedge would direct those bounces back out. So you can, I think you can kind of imagine a mechanical mirror like this. Throw that ball in, it goes bounce, 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 comes to a final mirror point and then bounces back out at you. That's very much analogous to what charged particles do on converging field lines. So that's concept number one, really important to understand. Any comments, questions on that? Okay, so let's see what that leads to. So radiation belts is one of the things it leads to, because magnetic mirroring traps charged particles on these so-called low latitude field lines. These are field lines that intersect the Earth at latitudes low enough that they don't themselves extend more than 5 or 6 Earth radii out into space. These are low latitude field lines. And charged particles are trapped on those field lines because they spiral around them. They go out into the region there where the magnetic field is small, and then they come in toward the Earth. The magnetic field gets stronger and stronger. They come to a mirror point and bounce off of that mirror point, go back around the entire field line, bounce off of the mirror point in the other hemisphere, and bounce back and forth. They're bouncing back and forth all the time like that. And so they get trapped on those. Collisions between particles will in general change their quote pitch angles. The angle, that's the angle at which the amount of a large pitch angle particle is a particle that's spiraling, um, that's not moving very fast along the field line. Most of its velocity is directed perpendicular to the field line. Low pitch angle particles are particles for which most of the velocity is directed along the field line. Low pitch angle particles will have mirror points that are much lower than high pitch angle particles. Collisions between particles will change their pitch angles, changes their velocity, they'll have different pitch angles, and that changes their mirror points. As long as the mirror points are well above the ionosphere where things start getting dense, the particles will rarely collide. Particles on those field lines almost never collide with other particles when they're well away from the Earth. The collision frequency maybe once every 10 years in places like that, but it rapidly gets much more rapid as you get into the denser parts of the atmosphere, including especially the ionosphere at altitudes of 400, 300, 400 miles, much more dense. And so collisions are much more likely. Any particle that with a mirror point below 400 miles will just get lost to the ionosphere. It just collides with other things. Now it's colliding all around. It's in the ionosphere. That's the end of it. But particles that have mirror points that are high enough can be trapped there for very long times. And the radiation belts are collections of high energy charged particles with sufficiently large pitch angles that they're stored on those field lines for a long time. The radiation belts are changing all the time because processes that we'll talk about, interactions with the solar wind, are constantly re-energizing, changing the positions of the radiation belts, occasionally generating new radiation belts temporarily. So the radiation belts are highly variable, but they are created by this mirroring process. comments on that slide?
Do these radiation belts affect telescopes that are trying to take images? So, you have a satellite or a telescope and it's trying to do something, and then bam, it gets bombarded by these things. Or do scientists take care to either put it way outside this range or way inside, like below the ionosphere?
I could always be wrong saying something like this, but I'm pretty sure this much at least is true. No optical telescope has ever been affected by the radiation belts. One, I guess I could barely imagine radio telescopes picking something up, but we didn't know about radiation belts until we put satellites up. The early satellites, one of the first things they did was detect this radiation that we didn't know was up there. So the Van Allen radiation belts were a result of kind of one of the earliest Explorer, I think, class satellites in the late 50s, early 60s. But no, so I think the basic answer to your question is no, but I suppose I could be wrong in some minor way. Besides, certainly in the case of the Webb telescope is not even in the magnetosphere, so it's not close to Earth, close enough to Earth. It's 1 million miles away from Earth, and it's not going to be affected by. It's not going to ever even see them because it'll never point itself at the Earth. Okay, so slide 12, getting close to the end here. The interaction with the solar wind. So what does the solar wind do? It does a lot of stuff. It is the central player in the magnetosphere drama. The solar wind is a high energy stream of ions. I think they travel at something like 400 kilometers per second coming from the sun toward the earth. They're charged particles. They run into the magnetic field of the earth, and the magnetic field deflects them because they're charged particles. That deflection corresponds to a current, and those currents generate their own magnetic fields that end up having the effect of confining the magnetic field of the earth into what we call the magnetosphere. It's very compressed on the front side. It's stretched out into a long tail that extends beyond the moon on the anti-sun side, and it opens up a cusp at about 70-degree latitude range, where there's the ability for solar wind particles to kind of directly enter and come down to ionospheric levels at about 70 degrees. As I say, a region called the auroral zone for reasons that you'll probably understand. That's a cusp in that. So all of that shape, the actual shape of the magnetosphere that you see there is not at all dipole-like. And that is completely because of the massive interaction of the magnetic field of the Earth with this high energy stream of charged particles shooting at it from the sun. Okay, I'll stop there for now.
So these particles, they're not technically radiation, they're just massive particles, right? And so, how
Well,
is
yeah,
it that they could interact with something that is not material in that manner to change its distribution? I can imagine, them following the lines and going through the Earth, but why would they actually change the shape of the magnetic field?
yeah. So this is one of the topics that I dealt with, in doing my thesis on the aurora. And it's a really interesting process. That'll be a little better on the next slide. Maybe, yeah. Let me just go to the next slide to answer that question, unless you have another question. Okay. So yeah, let's just look at slide 13 because it basically gets right at it. If you look at what's called the bow shock, the front end there, notice in this diagram, it shows what's called a sheet current. There's a very large sheet of current that flows from in that diagram, the far side of what's called the magnetopause, the boundary between the magnetosphere and the solar wind, from that far side over to this side. I guess that would be from the west to the east, right? A current flowing west to east as a sheet, kind of it's distributed over that entire front surface. And if you think about what that does, a current like that is going to create a strong upward magnetic field on the earthward side and a strong downward magnetic field on the sunward side. Think about your right hand rule. Point your thumb along that current. Notice that because that current is distributed everywhere, it's going east, west to east. Um, on the kind of interior side of that sheet, you're going to have a strong upward current, and on the sunward side, a strong upward magnetic field, and on the sunward side, you're going to have a strong downward magnetic field. Does that make sense? That's
Yeah, I'm just wondering
that
how
may
is the current flowing when there's no wire?
Okay, yeah. So just so that you see that. So number one, notice that what that does is on the earthward side, it makes the magnetic field stronger because it was already going upward. And on the sunward side, it reduces the magnetic field because it was going upward due to the Earth, and the sheet adds a downward field. In fact, to kind of first order, what happens is that sheet current eliminates the Earth's magnetic field on the sunward side and strengthens it on the earthward side. I am going to get to why the current is there in a moment, but I just want you to see that that's what that current would do. It would strengthen the magnetic field on the earthward side and eliminate it on the sunward side. In other words, it ends up kind of saying, no, there is no earth magnetic field sunward of that. And it's a little stronger than it would otherwise be because it's been kind of the magnetic field of the earth's kind of been compressed on the earthward side. Now, where does that current come from? Well, imagine positive charges being shot at the Earth from the sun. They encounter an upward magnetic field, and if you do that, if you take, remember the way we determine the force, the magnetic force on a particle, we put our thumb in the direction of the current. So we've got positive charges going toward the Earth. Point your right thumb toward the Earth in front of it. Point your fingers in the upward direction. That's the direction of the magnetic field that the Earth is producing there. And you'll see that those particles being shot at the Earth from the sun have a force on them from west to east. In other words, in the direction that that current is. So that what's making that current? That current is due to the magnetic deflection of the charged particles in the solar wind by the magnetic field of the Earth. It's a
Wow. So
complicated picture, but it's a wonder. I'll tell you the truth. The story I'm telling you now is the story that got me involved with my thesis advisor, because when I was doing my PhD qualifications, he kind of asked me about this scenario. He just said, suppose there's an upward field and a bunch of charged particles coming at it. What's going to happen? And I had to kind of had to kind of invent this scenario on the fly. I'd never actually seen it before. But it's a really beautiful example of the way everything you see in the that this was warped magnetosphere is entirely the result of currents that flow self-consistently to create it, to make it be that way. So it's a self-consistency argument between the forces in the solar wind, how they get deflected by the Earth's magnetic field, and what the net result is um, on the resultant magnetic field. The bow shock, in particular, the bow shock is one of the few places where you can really kind of appreciate that quickly. Other places in the magnetosphere, things get much harder to kind of visualize, but it's the same kind of self-consistent processes. So, yeah, sorry, I was talking a long time there. Go ahead, Shamash, if you have
no,
any other
I just
follow-up
want to follow
on.
up with one thing just to make sure I understand. So this whole picture is due because the sun exists. Without the sun, all of these particles wouldn't exist, and then we will see a uniform thingy, right? Or near uniform.
Right.
And
Yep.
so I'm wondering why, under this picture, the magnetic field of the Earth doesn't completely collapse or near disappear. Because, well, you have the magnetic field of the Earth, and then you have these particles coming, and they are generating this current that reduces the effectiveness or the value of that magnetic field because of the induced magnetic field they create as they create that current. And
Well, be a
so,
little
as the current
careful.
turns around, the magnetic field becomes smaller, and then the more particles come here, the more stress they add on that magnetic field.
Well, so be a little careful. Remember that deflection of the solar wind by the Earth's magnetic field creates this current, which then has the effect of strengthening the Earth's magnetic field on the earthward side and eliminating it on the sunward side.
Yeah, this is what I don't understand, because in my head, the lines are perpendicular from north to south when it comes to Earth. So if you're taking the Sun Earth line, I'm not sure how to put my right hand to see that happening.
Yeah. Okay. So remember that the pre-existing the dipole field of the Earth. Forget about the solar wind for a moment. Out there in front of the Earth's magnetic field is upward. It's from south to north, right?
Yeah, correct.
And then that sheet current creates its own field that's also upward on the earthward side of it. So the net magnetic field, due to both the Earth and that current, is
Isn't it
stronger than it
upwards
would have
everywhere?
been.
Like, why
So
would
it's
it change?
upward.
Because as
Well,
it's turning, if you turn around, so you have this black line on your diagram, right, with the XYZ. If you just
the
go on that
current.
line, yeah. No, not the current.
Hmm.
I mean
Oh,
the reference line. So it's
the reference line that goes through the
plasma sheet
Earth.
is written on it, and you know what I mean.
Oh,
You know the line.
okay.
Yeah.
Yeah, but
So
I don't want to. I don't want to really talk about what's going on in the
yeah.
magnetotail,
I
as
don't
it's
want to. I
called.
just wanted
Yeah,
to point the line to you so that you know what I'm talking about. So
right. Okay.
it's that line. So along that line, okay, you have an upwards magnetic field from the Earth, and you have a 90-degree rotating current, right?
Um. Well, so I guess I'm not sure. So once again, what you're talking about, so the thing I'm interested in is the arrow called dayside magnetopause current.
I see it. So this current turns around, doesn't it?
Well, so it does kind of wrap around to the side there, but I'm interested in what it does right in front of the Earth, right
Okay.
between the Earth and the
But
Sun.
why would it change its effect when it's the other side? So the 180-degree opposite side, what you call the
Oh, you
Earth.
mean when you're on the sunward side
No,
versus
we
the
are on the
earthward
sunward
side
side.
of
The
the?
arrow is drawn on the sunward side. No, because the
Well, no,
solar
the
wind is coming
arrow.
from there.
Okay, so the arrow is intended to be a sheet of current. It's confined to that blue surface.
Does the blue surface
That
turn around the globe to the other side or no?
Yeah, the blue surface is complicated and does a lot of things, but I'm just interested in the fact that there is basically a planar surface if you just confine your attention to the very small part of that blue surface that's right between the Earth and the Sun. It's essentially planar, right? It's just a small curvature surface that is perpendicular to the Sun-Earth line.
Okay, so the initial question was, if you just take that, then on that picture, as I understand, the induced magnetic field of the dayside current is opposite to the Earth's, so it weakens it
On the sunward
on
side
the
of it,
sunward
it
side.
is.
But then you
Right.
told me that on the night side, it strengthens
Not the
it.
night side. No, no. Oh, okay. I think maybe you're misunderstanding. So all I'm talking about is just earthward of that sheet. The magnetic field produced by that sheet is upward, just earthward of it. Not to the Earth, not behind the Earth, just earthward of that sheet, that planar current that's flowing
So
from
so
east to
closer to the
west,
Earth from that surface.
closer to the Earth.
Okay, what
Right.
happens?
Just earthward of that sheet. So if I just think about a plane, just imagine for a moment just a plane current. You just have a horizontal plane and current flowing away from you. But maybe that's the thing to do. Imagine a horizontal plane, current flowing away from you. If you point your thumb in the direction of that current, you'll see that above that plane, the current is to the right. And below that plane, the current is to the left. I mean, it's not the current, the magnetic field. Above that current flowing away from you, the magnetic field is to the right. And below that plane, the magnetic field is to the left because you've got all of this current flowing away from you. Point your thumb in all those directions. You'll notice that every time you're underneath that plane, your fingers are pointing, your right fingers are pointing to the left. Whereas if you try to ask what direction is the field on top, now you have to put your fingers on top and you see they're all pointing to the right. They all kind of add up to be rightward, a rightward magnetic field.
Yeah,
This may be a little hard to
yeah.
visualize because it involves superposition, the idea, thinking of that sheet current as just a bunch of little line currents and then adding up all of the contributions from all of those line currents. You'll have some in different directions, but the only things that remain are the parts that are perpendicular. So in this particular case, in this particular sheet current, just earthward of that sheet, it produces an upward field, and just sunward of that sheet, it produces a downward field. And the effect of that is to strengthen the Earth's magnetic field just earthward of it and to eliminate it just southward. So when we say the magnetosphere of the Earth doesn't exist out there, it doesn't because that sheet current has eliminated it.
Okay, I need some time with this. Sorry,
It
keep
is,
going.
yeah, no, I think it's completely, I'm sure you're not alone. I suspect there's a lot of people in the same situation. I probably should have had one more diagram here just to kind of talk about the idea that I'm talking about like a horizontal plane in front of you carrying current everywhere away, or, in the direction away from you. And what the net result of that is, how that produces a magnetic field that is all everywhere to the right above the plane and everywhere to the left below that plane. A sheet current always produces these counter-directed magnetic fields perpendicular to the sheet current on the two sides of the sheet. Anyway, maybe I can let that, we can talk more about that maybe in the thing. I'm almost done here. So let me just finish the last slide where I'm really not going to tell you anything other than to talk a little bit about this cusp. Showed that before. If you look at the magnetosphere, there's another diagram. It's not a great one there up at the upper right. There's this place on the sunward side where the magnetic field of the Earth stops going
John,
around.
John,
Oh,
your
am I gone?
your audio quality is very bad at the moment. So if you can do anything
Okay.
to, yeah.
Let me see. It's funny. Let me see what Wi-Fi am I? No, it should be good. Are you hearing me now?
Yeah, now it's better.
Okay. Yeah, I wonder what's going on. Okay. So on slide 5, I just want to kind of return to this cusp thing. If you look at any of those pictures, it might be better really to stay on 13 for a moment and just notice that cusp area there. What happens, part of the result of the interaction with the solar wind is that field lines on the front of the Earth, on the sunward side of the Earth, are kind of doing what they always do. They come out of the north, they wrap around the front, come into the sorry, they come out of the south, wrap around the front of the Earth, and then come in to the north. But at some point, there's kind of a last field line that does that. And there are field lines that emanate from the sunward side of the North Pole that are nevertheless wrapped around into the tail of the magnetosphere, opening up this cusp, a region of magnetic field that is open to the solar wind. Solar wind particles have direct access to the ionosphere down that cusp. and more generally have direct access to field lines that turn out to be at about the 70-degree latitude north-south. Um, Another cusp occurs on the south there too, so this is a symmetrical thing, and that ultimately is the kind of the primary reason we have aurora borealis in what's called the auroral zone. Aurora don't generally happen at the north or south pole, or the north-south magnetic poles. They happen about 15, 20 degrees off of the magnetic poles because that's where this cusp is. The cusp isn't at the north magnetic pole. It's a little sunward of that thing. And so on slide 14, I show a picture. There's another picture kind of showing that cusp in a worse way, but also showing the incoming solar wind particles. And then there's just a diagram kind of showing the general character of what's called the auroral oval. You don't see aurora at the pole. You see them off the pole in an oval that is centered on the magnetic pole, not the geographic pole. And that has different characters depending on what time of day it is, because of the fact that there's this asymmetry due to the location of that cusp. In general, you see kind of quiet, slowly undulating arcs in the evening. Around midnight, things get a little more chaotic. And in the morning, the aurora get kind of patchy. And won't even begin to talk about why that is, but it has to do with the fact that there is this, it matters where you are around the auroral zone just because of the fact that that cusp kind of comes in on the day side like that. You might think there'd be more aurora on the day side, but strangely, that's not the case. Even though there are auroras during the day, um, that's not generally the case that that's the most active there. But auroras in the auroral oval, auroras happen all the time. I went to Sweden two or three times. I can't remember now. I spent a month or two there each time and saw aurora basically every night because we were at a rocket base that was located where it was precisely because it was for auroral studies. That's why the rocket base had been built. So we saw aurora virtually every night. Okay, so I think that's pretty much it. As I say on the last slide there, we really have barely scratched the surface of the complex dynamics of the solar wind magnetosphere interaction, but there are just copious, of course, as with anything, online resources, and maybe you can use this if you're interested at all. You can search on some of the terms that we've talked about, get lots of great videos and other things. And I'm finished. We can have a little discussion.
May I correct myself, John? Thank you so much, by the way.
Uh-huh.
Yeah, so basically, what they observed was not the 12-year solar cycle. They actually observed what is referred to as the Gleisberg cycle that spans over 80 to 100 years. And
What is that?
sorry, come again.
So what is that? What did you call it?
The Gleisberg solar cycle. That's what they observed.
Gleisberg.
Yeah, the Gleisberg, because you see, they started. So for people who don't know the Gleisberg cycle, and I was one of them, it is just that cycle that is characterized by alternating periods of high and low sunspot numbers. Now they did not have that kind of technology to spot the solar wind or the sunspot numbers, but you see they using the Nilometer, that structure that you use to measure the Nile River floods. They began recording flood levels as early as the early dynasty, like 3000 BCE. So and we have evidence like the Palermo stone from 2400 BCE, right? So basically, their meticulous records spanning over millennia, that allowed them to indirectly say, know that their god Ra affected their life to the level that the Gleisberg cycle that spans over 100 years, as we said, affected the intensity of the flood. and that's something they had to be aware of for taxation. Yep.
I see. Yeah, no, I had never heard of Gleisberg cycle before, but I do under. I mean, I think I know. I mean, I knew that something like that existed. Um, I see a couple of actual publications kind of investigating the possibility there's a link between that and the Nile water level. I don't see specifically that the ancients thought there was, or maybe what you're saying is they just noticed a frequency and didn't. I don't think you'd be suggesting that they connected it to the sun because they wouldn't have known about sunspot numbers or anything. I don't think. Um,
Absolutely, absolutely. But we know that theologically speaking, they attributed everything that took place in ancient
oh,
Egypt to
just
Ra.
to the sun
To
god.
Ra. Yeah,
Yeah, that's
that's
true.
what
That
we
would
know.
probably be right. Okay, well, that's interesting. Yeah, no, I learned something there. Thank you. So anybody else? Anybody like to come up on stage and ask a question? I'm sorry, I haven't been looking at the chat. I don't know if there's, it doesn't look like there's too much there. Okay, that's good. I see somebody, I see Jay pointing out a long time ago that you couldn't hear me. Sorry about that again. I hate subjecting you to 5 minutes of silence. It's probably better than being subjected to 5 minutes of non-silence, right? Squeaky voices and all that stuff.
Question, John.
Hey, Jubin, go. Yeah, hi, Jubin.
Hi.
Sorry, yeah, welcome to the
Hi.
stage. Go ahead.
Yeah, yeah. I'm a bit confused about magnetic north and south pole. You mentioned change in magnetic north causes a positive electric current. My confusion is electrons which have negative charges, and when they move, they create magnetic dipole, north and south. Yeah. So how come then
Well, it's not
change?
quite that simple. It's not quite that
Yeah.
simple.
Yeah.
You have to have current
Yes.
loops
Yeah.
to
Yeah. Yeah.
create
Yeah.
magnetic dipole.
That's right. The current loops, electrons, they create, and they've got negative charges, and they create magnetic dipole, north and south. And how come then change in the magnetic north would cause the opposite charge, positive charge? I don't know. Like proton charge? Is that what you mean by positive charge? I'm confused there.
Yes. Okay. So I'm not entirely sure where you're going, but yes, there is in the case of electric charge, and this we have Ben Franklin to thank. He probably should have done it the other way around. But it turns out that the thing he called positive charge, we now know is the kind of charge that protons, nucleuses of atoms have, and negative charge is the kind of thing that electrons have. So there's that. And then there's um, the thing that we call the North Pole and the South Pole kind of play the roles of positive and negative in electricity, respectively. Not to say that they are positive and negative, not to say that they produce electric fields or anything like that, but they only in this sense that our conventional magnetic field in a magnetic dipole emerges from the North Pole and goes into the South Pole, just like our conventional electric field emerges from a positive charge and goes into a negative charge. But there's nothing really deeply significant. That's just all convention.
I mean, could it be that when what is meant by the positive charge that magnetic north pole creates is the direction of the direction that is sort of guides electrons, left and right or whatever? Is it the current direction of the current? Is that what it means by positive
Well,
and
so
negative?
Yeah, so there's lots of things that once you have the conventions, then there's lots of things you can say. When we talk about current, we mean the direction that positive charge flows, which is equivalent physically to the opposite of the direction negative charge would flow. So I can have a current in one direction due to positive charges moving in that direction, or due to negative charges moving in the other direction.
But what is moving is electron with negative charge at the end of it,
It
isn't it? Yeah.
right in wires, what moves is electrons, but there are solid state devices in which the thing that moves is a positive charge. It's a place that lacks, so there, I don't know if you've ever heard the word holes in
Yeah,
solid
yeah,
state
yeah.
type things. You talk about holes because it's literally the place there isn't an electron that moves. It's not really the electrons that are moving, it's the place that doesn't have an electron that is
Lack of,
doing the
yeah,
moving.
yeah.
Yeah,
Lack of electric charge. Yeah, yes, 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 yes.
right.
Thank you. Thank you anyway.
Yeah,
Thank you.
sure.
Thanks.
Thanks. Good question.
Yeah.
John, can I circle back to that Aurora Borealis thingy?
Sure. Love that.
So you have solar winds coming, and these solar winds have charged particles in them. I'm guessing this is hydrogen, helium, positrons, electrons, something like that.
Yeah, not so many positrons probably, but all those other things.
Yeah, okay. So as they hit this, what do you call it? The cusp in the and so that gap in the magnetic lines. What
Hmm.
really happens so that they produce these fantastic lights? Do they
That's
charge the air particles? That like air particles absorb them, or
Yeah, so that's a great question and a really complex. I mean, this is really the topic of my PhD research, and I haven't done it now for nearly half a century. So
oh,
I'm
I
by
feel
no
so
means an
special now.
expert. I'm no means an expert anymore. Um, but it just starts with the fact of that cusp. The cusp is important because it is a place for kind of direct entry of solar particles, but it's also a place where the magnetic field lines are kind of grabbed by the solar wind due to this kind of frozen in. A lot of plasma physics has to do with the idea that as charged particles move around, they drag magnetic field lines with them, just as the magnetic field lines drag the particles with them. So there's this kind of frozen in idea. And what happens right near the magnetopause is you get lots of disturbances. The magnetic field is being, rocked very violently by the interactions with the solar wind, which is right there. And those rocking motions get transferred down into the deep magnetosphere, especially near the cusp, because that's right where they're connected to the solar wind. And those energetic processes, then the fact that you're kind of taking a bunch of these lines and shining them back and forth really hard, it just deposits energy into the lower magnetosphere. And then the perennial question is that energy somehow is transferred to electrons, because aurora are the result of very energetic electrons, much more energetic than you see in the solar wind, slamming into the ionosphere. So what is it that produces these very energetic electrons? And the answer, it's been kind of understood for a very long time that it must somehow be the result of this violent interaction between the solar wind and those magnetic field lines, somehow turning into transferring that energy into electrons, which are then also directed in a very strange way directly downward. Like these electrons aren't mirroring, they're coming down along the field lines with very small pitch angles so that they can get down deep into the ionosphere and slam into it and create the ionization that then in recombination produces the light of the aurora. And early, when I was doing my thesis, the thing that was starting people were starting to understand was there were these what were called double layers that would form along magnetic field lines are generally very highly conducting. Particles can move, charged particles move along field lines freely. You needed some way to have a voltage drop along a field line to accelerate electrons into the ionosphere. And the thing at the time was to start understanding how you could create these kind of high resistance, what were called double layers along field lines that could then sustain voltage differences of like 20,000, 30,000 volts through which electrons would then be accelerated into the ionosphere. And I don't really know what the current state of play in all that is. But right around the time I was doing my thesis, people were starting to kind of see. In fact, my thesis was partially an attempt to look for the evidence of those acceleration processes. We looked at energetic particles coming straight down along the field lines in combination with probes that measured the electric fields and tried to look for these field aligned potential drops. So I don't know how
And
much.
the colors that we see are due to the gases in the atmosphere. So
Right.
mainly the nitrogen. That's what it is. Okay.
Well, and I can't remember exactly, but at one, so there are different colors, right? The fringes of the aurora are one color, higher altitudes are different colors. And yeah, it has to do with the concentrations of those gases at the different altitudes.
Has it been reproduced in a lab somehow, or this is just beyond what we can produce? Because I'm thinking if it's
Well,
just charged particles, I'm guessing we can do it, right?
in some sense, that's what a neon bulb, kind of a discharge bulb, is doing. You're just simply ionizing particles and looking at the light that comes from the recombination. So it's the same thing. That's certainly done all the time. We know the spectra of the elements because we can create discharge tubes in the lab and
Yeah, sure.
investigate them.
I'm wondering whether it's this idea of having a magnetic field where you can see it in small. Maybe I'm just
Mm,
thinking science fiction. So you can see it happening, but on small scale, right? So you can see
right.
this. You have a very big, let's say, Tesla coil, and it's just shooting stuff at some magnetic field, and then you can see the bow shock, and you can see all these things happening in a lab.
Right. So that's that kind of, if you're talking about that as opposed to the aurora, of course, themselves, the emission really doesn't have anything to do with the magnetic field. It just has to do with energetic electrons slamming into other atoms. But if you want to talk about things like the bow shock and how currents in plasmas create the very magnetic fields that contain them, all this kind of stuff, this is the heart and soul of plasma fusion research, trying to figure out how to create devices that will self-consistently produce the incredibly strong magnetic fields and make them stable against their numerous instabilities to keep a very hot plasma confined while never touching the walls of the container. Because if you want to create nuclear fusion, you have to make sure that these hot ions never touch the container, which is like, dry ice, right? It's so cold that you would instantly rob them of the energy you're trying to feed them for the fusion process. So all of those kinds of things, the current structures, the magnetopause kinds of things, magnetic mirroring. The first fusion devices were created by making what were called magnetic bottles. These were just strong cylindrical magnetic fields that got very strong at both ends, so that plasma would mirror at both ends of this cylindrical field and stay confined in this so-called magnetic bottle.
Wow, wow. All right. Thank you.
Uh, John, I've
Hey,
got
Juman.
further question about solar wind. In addition to electrons, will the solar wind include, does it include positive ions like proton or alpha particles?
Yes.
Uh, and so what would be would the effect of electron and the positive ions would they be different on the magnetosphere? How would
Oh, good.
how
Yeah.
differ how would it differ? You know, when it impacts the
Yeah.
magnetic field.
No, that's
So,
really a good question. The solar wind is fundamentally neutral. So, to the extent that it has positive charge moving at the Earth, it also has negative charge moving at the Earth. So, if you go back to that slide where I showed the current that I was talking with Shamash about for a while, when I first talked about it, I said, imagine positive charges in the solar wind encountering this upward field due to the Earth out there in front of the Earth. And I said those positive charges would be deflected into the direction of that arrow, self-consistently producing that arrow, producing that current. And that all sounded good. But what I didn't do was talk about, well, what happens to the negative charges? Well, if you think about what the negative charges do, the negative charges, if they come slamming into the front there, they're going to be deflected the other direction. So they'll be deflected opposite that arrow. That means they would produce a current in that same direction because negative charges moving the opposite direction also produce a current from west to east, just like the positive charges do. So whether they're positive or negative doesn't matter. You get a current west to east from both kinds of charges.
so thank you. So therefore, the aurora is the result of both electrons and positive ions hitting the atmosphere. Yeah.
No,
Uh,
it's actually not, because
all
it's
right.
for two reasons. Number one, the positive charges get accelerated by these structures upward rather than downward. The voltage drop that accelerates an electron into the ionosphere will accelerate a positive charged particle away from the ionosphere. So that's number one. And number two, well, I shouldn't say that. The speed, of course, would be. No, that's really it. They would get the same amount of energy from that structure, but because they're not accelerated into the ionosphere, they're not the ones that are doing the ionization.
All right. So just the electrons get through then. So I heard that the green color is the result of oxygen excitation by electrons hitting the oxygen atoms, and the red color is the nitrogen excitation. Is the question that Logic mentioned
Yeah,
it
I think that's right. And so if you've looked that up recently, I'll trust you. I just don't remember, but I think that's right.
So only electrons enter from the holes from the top and bottom, yeah, into the.
Say again.
So the conclusion is it's only stream of electrons enter the atmosphere from the north magnetic pole and the south magnetic pole of the Earth. Yeah.
Yeah, well, that's right. And I didn't mention, of course, is the same thing happens in the south. There are the aurora australis too, but there's very few people anywhere that can see them, because there's very little land down there in the southern auroral zone. But they are seen, and studied, and they're just like the north. There's nothing particularly different about them. They're both created by electrons. Auroras are created by energetic electrons slamming into the ionosphere. I should mention one other thing that's important for aurora. Um, the solar wind has an embedded magnetic field in it as well, and sometimes that magnetic field is upward, just like the Earth's magnetic field, so that when the solar wind and the Earth's magnetic field come together, they're in the same direction. Sometimes the magnetic field in the solar wind is downward, and so it'll be opposite the direction of the magnetic field of the Earth. And that leads through what are called reconnection effects to very different outcomes. When the magnetic fields are in opposite directions, a magnetic field of the sun can kind of connect to a magnetic field line of the Earth and drag it over the top or drag it over the bottom, and then you get a very different kind of an interaction with the magnetosphere than when the magnetic field's in the same direction. So that's a kind of a key distinguishing feature of different times. The magnetic field in the solar wind varies, um, not just with solar cycle, but just because we happen to be in the kind of equatorial plane of the sun, we can be in a region where it's upward or downward or to the side. It can be in any direction. That direction matters in terms of the interactions.
So would the storm be more severe if the magnetic field of a storm coming towards Earth is in opposite direction to Earth's
I
magnetic field? Is that
I
more
think
severe impact?
I think that's right, but I'm not going to swear to it right now. Andy, you
No,
had something
thank you,
too.
John. Thanks, John.
Yeah, I was going to ask when you said that Aurora Australis was more rare. Do you mean?
Only visible. People don't see it as much because there's not
Oh,
people
okay.
there.
That's. I thought they were
Yeah.
actually more rare for some reason.
Yeah, no, I
But
don't think so. I'd be
or is this
very
a
surprised if that were the
or
case.
is this a if there's no observer then it didn't happen kind of thing?
Yeah, that's right. I think that you could or you could, with some effort, you could make auroral sounding rocket bases like the one I was working out of in Sweden in the southern hemisphere, and I'm sure it's been done, but it'd be like Clauser, doing his entanglement experiment. Everybody knows what the result's going to be, so why would you bother?
Hey John, how you doing? I got a question. I actually
Yeah.
two.
Hi, Miguel. Thank
Um,
you. Yeah, sorry I didn't
it's
ask myself.
no. So question I have number one is out of the electrons, do we know what percentage of the electrons that are passing by actually strike a particular oxygen or atom in the atmosphere? Is it like a very small percentage or a big percentage?
Well, so just to be clear, are you talking about the electrons that come down to make the aurora, or are you talking about the electrons in the solar wind itself?
I guess I would be talking about both. Like, what's the occurrence? Is it like, is it 1 in 1,000 electrons strike an atom, or is it like pretty much all the
Well,
oxygen that's up there gets hit by an electron at some point or another?
I think it's probably fair to say that it's a good question. I don't know that I want to
Can you just
necessarily
start
stake
by
my
telling us
life.
what is the intensity, John, of this solar wind? Like how many particles per second are hitting that
Hmm.
front? Yeah.
That's a good question. So I'm trying to think. I mean, the density of, I think, of interplanetary space is, I think, maybe 10 or 100 centimeter particles per centimeter, cubic centimeter. Something like, let's suppose it's 10 particles per cubic centimeter. I'm probably off by an order of magnitude or two. But if it were 10 particles per cubic centimeter, that would be 10 million particles per cubic meter. Multiply that by 400 meters per second, and you're going to get, what's that? 2 or 3 billion particles per square meter. So if my original density and my velocity are right, you're going to get about 2 or 3 billion particles hitting every square meter of the bow shock,
Every
per
second.
second. Yeah.
Yeah, that's a lot of particles.
Yeah, that is
It's
a
it,
lot.
it is, but it's not, I mean, it is and it isn't, right? 2 billion atoms is you can't see two
Per
billion atoms.
second. Per second.
Yeah. Yeah.
And the other question I had, I wasn't here for most of your presentation, but I've always wondered: is the that high energy what's that high energy area outside of the Earth? Oh gosh, I had the name a minute ago and
I
I
mean,
can't. Van
you
Allen
mean
belts.
the radiation
Van
belts,
Allen
yeah.
belts. Are they in any
Mhm.
way related to Earth's magnetic field, or is it just completely?
Yeah, right. You missed the play. We talked about that briefly, and it has to do with this thing called mirroring that I talk about. If you go back through the presentation and
Okay.
back 5 or 6 slides, it has to do with the fact that uh, charged particles will bounce back and forth from the northern terminus of a field line to the southern, not terminus. from a mirror point in the north back all the way along the field line to a mirror point in the south, and they do this very quickly. That doesn't take them very long to bounce back and forth, and they'll do that for years. They can go for years without a collision. I I think that's right. No, maybe once again I might be saying something wrong, but I think that's right. That typical kind of period between collisions is measured in months, days, months, years, maybe, probably not decades. But these particles can be trapped on these field lines for very long times, and then it gets more complicated because they get populated with truly energetic particles via these magnetospheric processes that are once again somehow driven by jiggling magnetic field lines at the boundary between the solar wind and the magnetosphere. So it gets really complicated. Things back in the magnetotail especially get really complicated.
Cool, thanks.
Hmm.
Further question, John. Is that okay?
Uh-huh, sure.
Yeah, yeah, yeah. With regard to the sun's heliopause out there, that's where the solar wind and intersolar winds they equate in terms of strength. I was just a bit confused about why is the bow shock prior to that heliopause instead
Oh,
of being right at the heliopause. Why is it happening prior to heliopause?
right. Well, that has to do with, the kind of the same kind of thing happens with a jet, right? The shock wave of a supersonic jet isn't at the surface of the jet. It's out a little bit in front of that surface, right? The surface itself is the thing that the particles ultimately run into. But the fact that there is a thing coming, that's going to, it's going to really slam into them gets communicated out a little bit in front by kind of acoustic processes, if you want, wave processes, communicate. So the solar wind knows it's about to run into something, run into that place where the current ends up happening, where the magnetic field is the thing that really deflects the particles, before they actually get there, for the same kind of reason. I don't know if that makes any sense, but the shock wave of a supersonic aircraft is out there in front of the aircraft. How did that happen? It's the same kind of process.
Thank you, John.
Hmm.
I got a question about the magnetic field again. Does cosmic rays affect it in any way? Let's say if we were to take out the sun out of the equation, is there any like added from cosmic rays?
Yeah. Well, so cosmic rays would do the same kind of thing. They would get deflected by the magnetic field and produce a current, but there's not enough of them to do very much. I mean, if the modification of the magnetosphere was just due to incoming cosmic rays from intergalactic space or whatever, it wouldn't be a very big modification of the magnetosphere. Solar wind is just a very, relatively speaking, a really dense, uniformly moving plasma, and it makes a lot more has a lot more effect. Andy, I saw you unmute again.
Oh, I ejected myself from the room for some reason, but
Oh,
I think you want to make the comparison to a subsonic airplane because on a
uh,
supersonic airplane, the shockwave is in fact right on the plane.
is that
It's
true?
behind it, yeah.
Oh, okay. Well, then that answer, that's interesting. I didn't know that. Um, okay. Well, my answer was shit then, if that's
Well, it
true.
just replaced
Uh,
super for sub, and it's all good.
Well, I suppose that's true, and I guess maybe that's the question: is in what sense is the bow shock a quote supersonic? I guess that really is. You're right. In fact, it's just a solar wind, coming up on the magnetic field of the Earth, and the only reason it can be out in front, I guess, is because acoustic waves can travel out there in front of it to make it known before it gets there. Yeah, good point. But that is news to me, I guess, in a way. Somehow I thought even a supersonic jet somehow communicated out in front. I don't know how that would happen now that I think about it.
spooky action, probably.
Yeah, well, I think that's probably was thinking of entanglement. Well, okay, you guys, I'm getting ready to shut this thing down. I'm willing to entertain a question or two,
That sounds
but
spooky.
shutting it down.
Yeah.
It's spooky for you because now you have to find another place to go.
You have to shut it
No,
down and keep it open at the same time.
I can create a. I'll create a room. You guys can.
Well, okay. Yeah, so, going once, twice. Shamash, are you gonna do a philosophy thing next week?
No, unfortunately, still on pause.
On
No
hiatus?
philosophy on Wednesdays. However, you have Sam's rooms on Tuesdays. IP law. Again, I'm totally not the person to be interested in this. However, this is very fun. This has been fun, and Sam is doing an amazing job discussing what is it?
Intellectual property.
Intellectual property law. So if you're interested in that, that's every Tuesday at 12, I think, Eastern, if I'm not mistaken. It's either 12 or 1 Eastern. And you have on Thursdays as well, uh, the chemistry rooms. So that happens, I think, 2 p.m. Was it John yesterday?
Well, okay, so it was 1 p.m. Pacific time, so 4 p.m. East Coast time, 2 p.m. Sam's time.
2 p.m. Sam's time. Okay, cool. and and on Friday you of course have John's Bite of Physics. That's 17:30 GMT. So is it 9:30? No, that's
9:30, yeah, 9:30
yeah,
Pacific time. Yeah.
Pacific. Exactly.
Same
Okay,
as
cool.
same as yours on Wednesday.
Exactly. When we restart. So yeah, you guys are well entertained in my absence, and yeah, I'm not really necessary here. I'm just latching on your backs.
I'm just trying to think. I think I going to be on hiatus next week? No, I should be back next week. Okay, yeah. So, okay, very good. Any other last words?
What we will do very soon is create a schedule for these rooms on the Scientific Discourse currently dead Discord group. So if you're on Discord and you want to know all the updates, um,
Mhm.
you can follow the link I will paste in chat in a minute, and you can join to just keep no because we do a terrible job um, broadcasting and telling people what is it that we're doing. So if you want to know and you're interested in these rooms, just give John a follow and join the club here. And of course, subscribe to the YouTube channel.
All right, thanks, Shamash. So I'm gonna leave you with a song I played a couple times before. This is one of my favorite tunes from a band I used to be in once again about a half a century ago uh, with a guy named Mike Johnson. It's a song of his called Borderline, and I'm the electric guitarist in here. So we will see you again next week, hopefully. Thanks for coming, everybody.